Good afternoon, everyone. I'm Muyao, currently a master's student from Tsinghua University. It's a great honor to be here amongst you today and a privilege to share our paper, Mixed Reinforcement Learning for Efficient Policy Optimization. I will introduce our work from the following aspects. Intelligent vehicles are advancing at a fast speed, and decision-making for the automated vehicles is the core of vehicle intelligence. Now it faces so many challenges, such as road complexity, traffic dynamics, and behavioral randomness. Therefore, intelligent vehicle needs higher-level intelligence. Reinforcement learning is one of the many popular methods that could develop a self-learn ability for the autonomous car. Historically speaking, RL is a bio-inspired algorithm which mimics learning behavior of an animal. It repeats behaviors that result in rewards and avoids behaviors that result in punishment. In theory, there are two basic ways to apply RL in engineering. The first one is offline training and online implementation. The second one is online training and online implementation. Reinforcement learning can be generally classified in two types: data-driven RL and model-driven RL. The data-driven method uses real interaction data to represent system dynamics. It has the best final policy accuracy and the ability to solve the complex environment. However, it has low data efficiency and needs a large amount of interactive data. The model-driven method uses a word model to represent the system dynamics. It has high data efficiency and needs less interactive data. However, the policy accuracy will be damaged due to the model error. So combining the data-driven method with the model-driven method is critical to search policy efficiently and accurately. It has several challenges. How to represent the dynamics of the stochastic system accurately and ensure the convergence and stability during the policy optimization are two crucial issues. Here we will introduce the mixed reinforcement learning algorithm used to tackle the aforementioned challenges. We consider a discrete time environment with additive stochastic uncertainty, and its actual dynamics are mathematically described as follows. The fxu is the certain part, and the kc is the uncertain part, which is used to represent system uncertainty. In mixed RL, the environmental dynamics are dually represented by both an analytical model M and state action data D. The former represents the designer's knowledge about the environmental dynamics. It is defined in the whole state action space and can be used to accelerate the training speed. The latter comes from the direct measurement of state action pairs during learning. It is generally more accurate than the model, and therefore can improve the estimation of the uncertain part in the analytical model. We solve the posterior state transition probability under Bayesian estimation framework by taking the empirical model as prior knowledge and the state action data as evidence. Such a mixed representation can accelerate the training process compared to purely data-driven RL, while achieving better policy satisfaction than the purely model-driven counterpart. The objective of mixed IL is to minimize the expectation of cumulative cost under the distribution of additive stochastic uncertainty C, shown as the fourth equation in this page. By using Bellman's principle of optimality, we have the well-known Bellman equation similar to other IL problems. Mixed IL aims to find an optimal policy by solving the Bellman equation in an iterative way. The performance of the generative policy depends on the accuracy of the representation of the environmental dynamics. Traditional IL algorithms usually involve policy evaluation and policy improvement, two steps. Different from them, mixed IL consists three alternating steps: iterative Bayesian estimation, policy evaluation, and policy improvement. That is equal to the IBE, PEV, and PIM. The iterative Bayesian estimation is used to estimate the mean and covariance of the additive stochastic uncertainty iteratively. PEV seeks to solve the self-consistency condition under the current step policy pi and the estimated uncertainty C. And PIM is to search a better policy by minimizing a weak Bellman equation. The first alternating step is iterative Bayesian estimation, which aims to maximize the posterior probability with collected data and prior information. In general, we introduce P-mu and P-kappa as the prior distribution of the mean and covariance. Then use the IID assumption. We can obtain the posterior distribution in an iterative manner, which aims to reduce the calculation complexity. Intermediate variables are used to store the information of historical data, and the new estimation results are derived by both the newly collected data and the intermediate variables. The second alternating step is PV, which aims to solve the self-consistency condition under the current estimated distribution of the uncertainty C. And the third alternating step is PIM, which aims to find a better policy under the current estimated uncertainty C. Prior works proved the convergence of alternative optimization between the value function and policy in traditional IL. However, the learning process of mixed IL is quite different from traditional IL. It alternated among three key elements: the value V, the policy pi, and the uncertainty C. Here we give the proof to the convergence of mixed IL, as the IBE could converge with probability 1 with Kolmogorov strong law. We can prove the state value is monotonically decreased and bounded during the iteration under the mixed reinforcement learning framework. Then the convergence of mixed IL can be proved. For comparison purposes, a double-line change task is simulated respectively with mixed IL and other four typical IL algorithms. The task is to track the desired trajectory in the lateral direction while maintaining the desired longitudinal velocity under the longitudinal interferences. Here is the architecture of the neural network and the setting of hyperparameters. In 20 different testing experiments, the mixed RL outperforms the other algorithms by having a superior convergence rate. It converges almost twice faster than the ADP with the learning model, which confirms the effectiveness of the designer's knowledge embedded in the mixed representation of the system dynamics. As shown in this page, the mixed RL has the minimum longitudinal speed error and the minimum steady-state lateral position error. In summary, the mixed RL exhibits the fastest convergence speed during the training process and superior control performance in the given double-line chain task. At last, I will give a summation and future work about our research. This paper proposes a mixed reinforcement learning approach with superior performance on convergence speed and policy accuracy for nonlinear systems. The application of the mixed RL to more general environmental dynamics and non-Gaussian and uncertainties will be investigated in the future. Thank you for your attention, and if you have any questions, I would like to answer it. Thank you.